Hello everyone, this is John. I'm back, and today we're going to do some projectile motion problem with regards to the Martian. So last video we explored the gravitational acceleration constant on the Martian surface by using the universal law of gravitation as well as the Newton's first law. Well, today in this video we're going to explore something a little different, something a little more fundamental, which is kinematics. So as for kinematics, we in grade 11 we learned the projectile motion, where we have to basically calculate as an object is free falling and eventually landing on the ground. We had to basically calculate the V2 or V1 or the height, max height, for example, the maximum height. And today, on the contrary, we're not going to get the height, but height will be given. So we are now going to start. I'll move the camera a little bit just to make it more clear. So we do know that after the launch of the Mars ascent vehicle, it burns till t equals to 30 seconds. So these rocket engines burn until 30 seconds. And then there's MECO, which means, main engine cutoff, a common terminology used in rocket science. And from here, we enter a free fall. The Martian surface of Mars. So if you guys can see, so recall a scene where a Mars. So this is my last video, and the speed is about. It's hard to tell, but the speed is about. So the speed is about. Let's actually calculate the speed. You know what? Let's just do this by hand. So about 10 seconds, I feel like it does reach approximately 1 kilo above the surface. So we're just gonna say t equals to 10 seconds and d2 equals to 1 kilo, which is 1,000 meters. Let's just say Saturn V acceleration in meter per second squared. Okay, so for Saturn V, we're just going to use Saturn V as an example because Saturn V has more transparent data. So, because it's really, really old. So Saturn V is, the first stage of Saturn V is, the acceleration of it is about 120 meter per second. And, okay, so let's just give it like 150 because Saturn V is insanely, the acceleration is pretty slow. So we're just going to say 150. And we are dealing with projectile motion, so we do have to deal with what the V value, so we're trying to, the whole thing we're trying to do here is we're trying to get the V2 value, which equals to the V1 value in the projectile motion, while during a free fall. Here, this thing is, at the period where the rocket is boosted by, it's this propulsion system. So, okay, so kinematics formula. So we got the acceleration. We just have to get the value of V2. Okay, so back to the kinematics formula. Which kinematics formula can we use in this equation? So very simple. We have to use. We got displacement. We got time. We got everything. V1. We're going to use the V2 equals to V1 plus AT. I'm not sure if you guys can see this. Let me take a look. Yeah, it's a little bit here. There you go. So yeah, V2 equals to V1 plus A2 formula. So in this case, we do not know what the V2 is. V1 equals to 0. So we're going to cancel out V1. And we just need acceleration, which is 150 meter per second times, multiplied with time, which is 10 seconds. So V2 will equal to, so V2 will equal to 115,000 meter. Well, that's going to give the displacement, though. Okay, so V1 meter per second. So times, this is meter per, okay, so that's going to give meter per second. Oh, I see. Okay, so I made a little mistake here. This has to be squared. My bad. So yeah, this is going to be meter per second. So this is going to be the value of V1 in the projectile motion. And we didn't really need the displacement here. We just already got the V2 number. Okay, so I'm not sure if it's normal. Okay, I'm just going to convert that meter per second to kilometers per hour, because that's insanely fast. Rocket speed. Let's see. Okay, so this is normal. The speed of a Saturn V first stage is about, when it comes to, when the first stage is burning, is about 2,756 meter per second. So this is quite normal for this Mars ascent vehicle to have this kind of speed. It's not a crazy number, so I just checked it. So we're going to use this as the V1 value in the projectile motion we're about to calculate. Let's just say after 10 seconds, right? After 10 seconds, you know, after it accelerates, you know, full throttle till 10 seconds, and then the rocket transitions into, you know, a cruise mode where it kind of maintains this speed instead of accelerating even more. So let's just say, yeah, V1 equals to 1500. So I'm just going to give a little more explanation here, that until T, so when the rocket reaches T equals to 10 seconds, rocket stops accelerating and it enters a constant velocity, you know, constant v, right? So here, I know it's a little bit unclear. There we go. I'll move it a little bit and we'll zoom out a bit. Yep, so okay, that's clear. That's clear enough. Alright, so now we got the value of V1, which is we took forever in order to accurately predict the number, the value of it. Now we can just simply plug in the number in the equation, which we're going to use here, V1. So here, V1 equals to 1500 meter per second, you know, and here we're going to go through a process called MECO, which, you know, in this, so here it's constant velocity, right? And throughout this process, it's accelerating, you know, by 150 meter per second squared. Yeah. So here we got every value that is needed, and your V1 equals to 1500 meter per second. And what is V2? Since when we reach the highest point in this kinematics, so when we reach the highest point in this projectile motion, you know, V2 is going to be 0. As when a rocket kind of, you know, goes into free fall, you know, and it's going to lose velocity due to gravity, and then it's going to fall. So it's going to be, the V2 is going to be 0 here, and V1 is going to be 1500 meter per second. And do we know the horizontal displacement? Not horizontal, my bad. The vertical, the height when it's when it reached the highest point. So that's also hard, because like until t minus 30 seconds, we do have to calculate the displacement, and we have to get the average orbit, like the orbiting altitude, where most spacecrafts that go to Mars orbit, like the minimum altitude, and then we have to kind of subtract the value of the displacement from that. So that's going to be a little painful, but let's do this. All right, so or I'm not sure if there's an alternative option. Okay, so here we go. We got the V1, V2 projectile motion. So we do know the A, right? A is, we got the constant last time, is negative. So A equals to G, which is negative 3 we're using negative value because it's, you know, it's acting downwards, not upwards, in the opposite direction. It's a vector. It's a vector quantity. So the G is 3.71, which we derived before, but 1 is kind of a small value, so we're just going to ignore that. So we're just going to go with negative 3.7 for convenience sake, just for to make calculation easier. And okay, we're going to draw a new diagram here because this is a little too messy right there. So here we're going to reach the max point. So max point. I'll just move the lighting a bit just to make it a little brighter, easier for you guys to see. And then we do know the H value, which we're going to calculate. Okay, so the average, okay, Mars orbital altitude. Okay, so let's assume that this spacecraft has to go all the way up to geostationary orbit. You know, geostationary orbit is basically, to simplify, when you're orbiting a planet, like, assume that's Mars, and then you're kind of orbiting, right, like that, and this is a satellite. No matter like where you are, it's always going to face the same ground. So essentially, you have to match the speed of its, spin to the orbital velocity of the spacecraft in order to continuously face the same ground. So kind of like that. So just say this is where an astronaut planted a signal relay to continuously face this ground. You know, this speed, like the speed of the spacecraft, has to match the speed of the spinning speed of the Mars has a planet. So this is basically what geostationary orbit is. And the geostationary orbit altitude at Mars is 13634 kilometers. We have to change that to meters. Actually, let's assume that the spacecraft has to go like a little closer to the Martian surface, which is 3,000 kilometers, because the previous value is based upon the fact that the spacecraft has to orbit outside of Deimos, which is one of the moons that is spinning around. So here we converted the value to meters, and we just have to subtract the total displacement that we already covered by rockets, on propulsion, so that we can solely focus on the area where free fall happens. And to recall, as you can see, free fall only happens after 30 seconds, after the launch. So right there, and between 10 seconds to 30 seconds is constant velocity. Before 10 seconds, but rocket accelerates at a rate of 150 meters per second squared. So that's the things we already have. And all right, so we do have to get the displacement. All right, so we do not know the displacement. We have like two segments because we have parts that the rocket accelerated at a constant velocity. Let's just do constant velocity part first then. So as for constant velocity, when the rocket is constant velocity, it's between 10 seconds to 30 seconds. So 30 minus 10 equals to 20 seconds, which is going to be the value of delta t. So yeah, we're just gonna get the displacement that while the rocket is in constant velocity, that the rocket covered. Okay, so delta t equals to 20 seconds, and other than that, we do need a little special formula. Okay, so v1 and v equals to, we don't need any special formula actually. V equals to 1500 meter per second, and we just have to multiply. So here I'm gonna say t equals to v equals to d, which is gonna be 15. Sorry, my calculator is just really weird. Okay, so 1500 times, so 20 seconds equals to 30,000 meters. So that's that's what we covered while the rocket is in constant velocity. And last but not least, we have to, so this is value 1, and last but not least, we have to guess or calculate the what rocket covered while it is accelerating. So as you guys can recall, here, right there. Okay, it's a little bit tiring, I know, but hang on there. We can figure this out. So while rocket is accelerating, v1 obviously 0. V2 is, well, it's v2. Okay, 1500 meter per second acceleration. We also do know the acceleration, which is 150 meter per second squared. And what's the time? Time is 10. We accelerate for 10 seconds, right? And we have to just know what the displacement is, right? So, okay, so we're just going to use the value of acceleration and displacement to get the d value. Okay, so one of the formulas we also learned in grade 11 physics curriculum is, okay, so we're using the formula, v2 squared, v1 squared, 2ad, because that involves everything, right? Except for the time, because, but we don't really, I don't think we really need time here. We're not going to throw another variable. So, okay, so another variable, right? 1500 squared, just throw in the values, and we'll cancel since it's d1 0, and 2a, which is going to be 150, and displacement we do not know. So in order to get the displacement equals to 1500 squared over 2150, which is going to equal to 1500 squared divided by 150 is going to be 1.69 times 10 to the square of 1, 2, 3, 4, 5, 6, 7, 8. So 8. And that's meters. Okay. Yeah, so that's the displacement we covered. So, okay, so final. The displacement in the projectile motion is geostationary orbit altitude, which is 3.0 to the power of 10, 3.0 times 10 to the power of 6, which is in meters. So geostationary orbit altitude, right? Minus. So the displacement we covered while rocket is accelerating, which we derived on the bottom, which is 1.69 times 10 to the power of 8, also in meters. So everything kind of matches up. Wait. How is that a bigger number compared to 1.69 10 to the power of 8? That's not right. That is not right. Okay, so I'm just going to see what is wrong with this. Okay, 10. I'm just going to convert that to, okay. One, two, three, 4, 5, 6. So that's meter. Okay. 2 kilometers. Okay, that's it's very significantly bigger. So okay, so we made a mistake in the previous question actually, where we wrote this thing. This is not right since it's way too big. So we're just gonna fix that real quick. Okay, so oh yeah, I know where I made a mistake. It's the computation error. I forgot to add a bracket. So it's supposed to be 7. Yeah, it can't be a value that is that huge, that humongous. So it's gonna be 7,500 meter, and so it's gonna be 7,500 meters, which is what we covered while the rocket is accelerates, and then minus what we covered in while the rocket is in constant velocity, which is going to be 30,000 meters, right? So we pretty much covered it all. So last but not least, we have to actually calculate the value of it, which is going to be a very interesting number, but we'll see. So 7,500 and 3, 1, 2, 3. Okay, so the value is going to be 2962510 meters. Okay, so that is the altitude we have to reach. That's the total height in the projectile motion. And so we're going to label that as height. It took us forever. So here we're going to label that meters. And what we have to do is we have to calculate how long it takes to reach that height. Just without any kind of external propulsion or anything like that, solely by projectile motion, obviously. And yeah, I think that's about it. Yeah, that's about it. Okay, so the way we're gonna deal with this question is we're gonna erase the majority of the equations we wrote since we're running out of space. Okay, there you go. We kind of cleared up everything. We just got this little thing left, which we have to solve. Okay.